Check one, one, one. Hello, hello. Check one, one.
New services, new products, which was beneficial for this company, and that's why it's getting a lot of traction nowadays, and everyone is following that trend. So in IT and CS classical domain, this trend is going to increase, and a lot of other companies are following because they see a value. For example, in Facebook, if you see targeted ads, if you're searching something, they will give you something which is related to what you might have seen. That is essentially done by a machine learning algorithm. Netflix, if you watch a set of movies, based upon the set of movies that you have watched, Netflix will recommend the set of other movies that you can watch. That's essentially a machine learning working right there in the product that you can see, right? Marketing, Google, right? For depending upon search that you have done, it will do a very targeted marketing of what should be the product that should be displayed on your screen and so on. So all these companies are using machine learning algorithms in their product, and that makes a business case for them, and that's why this is gaining popularity. But what I want to show you is like, okay, that's fine. We will have classical software and other things, but looking 25 years from now, where is the scope of data science, machine learning, and AI? And that's the focus of my talk. And I'm arguing that focus is going to be on cyber physical systems, and hopefully you will get that notion by the end of this talk. Okay, so design, I'm going to talk about the domain that I work. So this domain is essentially about dealing with CAD. How many of you have used any CAD software like CATIA, SolidWorks, or anything like that to draw 3D models? Okay, very few. Okay, that's good, because then this is a new information and hopefully a useful information for you, right? So typically, whenever we are making a product like anything that you see, laptop or keyboard and other thing, they has to be drawn in actual software before you can fabricate them. So those are CAD models, and typically when you see the CAD models, they are designed by some person who has abstracted it, and then that is converted into computers. But the computers, in this case, when they are using the software, they are not intelligent. They are dumb. They are only storing things. But here, what we are trying to do is we are trying to make computers smart and create machine learning-based algorithms that allows people and machines to become more intelligent and interactive. That's one. And the second is, which I think hopefully you will realize, that most of the times when you're interacting with your laptops and stuff like that, you are using what is known as WIMP, which is Windows Icon Menus and Pointers. So you will click something in the menu and you will drag something. For example, if you're doing PowerPoint. So this interaction is very mundane. How can we use machine learning algorithms to fundamentally interact in a completely different way? So those are the two things that I want to talk about. And this is an area I worked for 6 years in terms of research. And I have published 25 to 30 papers in that domain. I'm picking a couple of projects in that domain to show what is happening. So what you're seeing in the screen is we have created an interface where you will see we want to creatively generate 10 different concepts of table, 10 different concepts of power screwdriver, or 10 different concepts of aeroplane fuselage, right? And this is something that we do in engineering for sure. So what is happening in this interface is, depending upon what you see in the main screen, which is the partial subassembly, you will see a set of part in the bottom is automatically populated. So depending upon what is there in the main, this set of parts is being populated by a machine learning algorithm called probabilistic factor graphs. Okay, so all the reasoning we are doing, and why we want to do that? we want to learn from the set of parts that has been used previously in different designs of tables, and using a machine learning algorithm, we want to provide some intelligent suggestions for the human person who is doing the design itself, right? The suggestion you get in the bottom is essentially a machine learning suggestion of top 10 parts which could be attached to the partial assembly, and that will help you in creating the design. Now you can see now we moved away from the design of tables to design of power screw, which is basically a power tool. And if you want to do that, if I'm designing it, a person is trying to come with the conceptual idea of it, how can we take a machine learning algorithm and a set of designs that has been used in the previous iteration to suggest and enhance the creativity of a human person. So if you have come across, there is a whole area which is known as human computation interaction, SCI, or human machine interaction, HMI. Those areas are essentially where a person is interacting with a computational algorithm or a person is interacting with a machine, and they together are solving a problem that none of them individually can solve. So this is essentially a human computation interface which is acting where human is basically selecting the part, but the intelligence is provided by the machine learning algorithm to draw different things and so on, right? So this is one application where you can see machine learning is making the computer more smarter. Okay, so let's move on to the second application. In this application, what we are doing is we are trying to fundamentally change the way we interact with the computers and so on. Even though this application domain is controlling what is known as Google SketchUp, and Google SketchUp is a Google software that is used for drawing 3D models and so on. So what you will see here, the student who created this interface, he has what is known as a BCI, or a brain-computer interface, that he's wearing, and this BCI has 6 different sensors in 6 different locations, and these sensors are used to read the brain signals that are emanating from that student itself. Now what we do, we use some signal processing, and on top of that signal processing, we are using classical machine learning techniques like random forest to classify what that user is thinking in terms of a command. And if you are able to do that, what we can do, we don't need to no longer control and use any mouse to pick anything. We can think about different commands, and that has been converted exactly into what we want to do with our hand. And this way, we are drawing things, or we are creating 3D models by just thinking about them. So we don't need any interaction. We don't need any hand, mouse, and anything. We can control by just thinking about and changing that interaction. We can fundamentally change how we interact with different things. At this point of time, I want to mention that this is also a very big area that is growing, that is going to be creating a lot of products and services. Specifically, if you think about, and this is the work we did in 2012, 2013 timeframe, so that it took another year to publish it. But nowadays, this field has moved fast, and you have a lot of sensors which you wear on your wristwatch. There are the wearable sensors. If you are wearing any smartwatch, there are a lot of sensors that are out there. And so we are moving where sensors will be mounted on the human body, and you can do very beautiful things, and you can create new products, new services out of these systems. For example, you can monitor, work rate, and now there are recommendation algorithms that tells you that what kind of exercise that you need to be doing, how much you should be standing, how much you should be traveling by just wearing a glass. In fact, some of the research recently has done something like this, that Apple has been able to place hundred thousands of watch on different users, and they have collected a lot of data where these data are being used to do prediction when you might have heart attack and so on. So based upon 2 hours, 3 hours previous users history, people are thinking about predicting whether you might have a heart attack in next 2-3 hours or not, right? And if that is the possibility, then you can basically take preventive measure, and you can save different lives and so on. So this whole idea of BCI, IMUs, and different sensors on the wearable is about collecting data, and if you want to process that data and do something intelligent with it, then obviously you have to do data science, machine learning algorithms to use that information to create services and product. And lots of these services and products are non-existent right now, but this will be the focus of many startup companies going forward, where they will be thinking about using machine learning algorithms for this very, very innovative set of products that they might have. Okay. So let's move on to this discussion, and I want to quickly show in the manufacturing domain, right? This is the base of my laptop, and somebody needs to be actually fabricating this. And typically how this is done is you might have an experienced machinist who is looking into these features like slot, keyways, and so on, that needs to be machined, right? And based upon this, he decides that I need to pick a specific machine tool and I need to solve this problem. Now, what we want to do is we want to replace this machinist by a machine learning algorithm so that all of this could be automatically done, okay? And this is a problem that you might be also doing on your daily life, so let me give you that example. Let's say if you're using PowerPoint slide for drawing a figure, and if you have a notion of what that final figure should look like, then what you do is, in order to draw that final figure, I need to be, taking this rectangle, bringing that rectangle in the center of my slide. Maybe I will be picking an ellipse. I will bring that ellipse close by. I will take an overlap, and that overlap will give me the final figure that I might have in my mind. So when you're doing that, you are essentially solving what is known as two-dimensional feature recognition problem. You are recognizing the features of what is there, and you are taking those features and you're drawing different things here. This is the three-dimensional version of those feature recognition problem, where your features are three-dimensional and you're trying to recognize these 3D features and so on, right? So again, what we did is we created a machine learning algorithm, and this machine learning algorithm allows us to automatically, first of all, in order to create this algorithm, we created a unique data set. And once we created this unique data set using a set of new techniques in the deep learning domain, which is known as three-dimensional convolutional neural networks, we are able to create a machine learning algorithm that can automatically recognize different types of features that are there on the part. And if you are able to recognize that, you can do automated planning and so on, where you can create exactly what is the best way to manufacture that part, right? So here you can see an application of machine learning in a manufacturing domain, which is a non-traditional domain or a cyber physical domain that we say. Okay, so I will skip this and I will move on to some other interesting things. Here is use of machine learning in 3D printing domain. How many of you are aware of 3D printing or additive manufacturing? Okay, a lot of you. That's very good. Okay, that's very, very good. So 3D printing is a new type of manufacturing technology, and they are mostly open loop, and especially if you're printing metallic parts using 3D printing processes, you need to monitor them. So this is a whole area called process control, and in order for you to do process control, you need to use some sort of computer vision of techniques where you're placing a camera to monitor what is happening inside the process, and then using machine learning algorithms like CNN and so on, you can classify what is the current state of the 3D printing process. Now, what we have is, in this process, what we want to do is we want to recognize one of these three states. Okay, so one of the three states are known as undermelt, beautiful weld, and overmelt. So what is happening when you have undermelt? You are essentially not providing a lot of energy, so things are not fusing, and you are not able to build a good quality part. Whereas in the last case, where it's overmelt, you're providing a lot of energy into the bed, and it's essentially burning things, and things are not joining properly. And in that case also, you will have a part which is fabricated, but it will be defective. So we want to be somewhere in the middle range, which is known as the beautiful weld, where we are not supplying too much energy or not taking away too much energy. So how do we go there? So one thing that we can do is we need to first use a computer vision or a camera to find out what is the state. And if the state is undermelt, then we can change the process variables and we can increase the amount of energy that is going, and that will bring us back to the beautiful weld. Or in the other case, when we are supplying too much energy and burning things, we can reduce the process variable and bring it back so that we are in the beautiful weld. Now, how many, as I mentioned, like some of you know about machine learning. One of the things that I want to point out, if you are in the data science and machine learning and AI domain, is sometimes people will think that we have only 3 classes, though this might be a simpler problem, and typically the more number of classes that we have, that will be challenging. But that's probably not the best way to judge about the efficacy of machine learning and AI algorithm. What you should be always thinking about when you're thinking about a problem that could be solved using machine learning, data science, and so on, how can I compare the performance of that algorithm with a human performance? Okay, and I will give you an example. A lot of data sets that are there in the computer science domain. They have hundreds of different classes to identify. For example, they want to identify cat, mouse, dog, car, pedestrians, cycles, and so on in images, and that's a classification problem known in machine learning domain. And they have thousands of different classes that they want to identify, right? Whereas we have only 3 classes in this problem. So if you take the performance of the current generation machine learning algorithm, they are very, very accurate. If you have a large amount of data, 99.9% accuracy. But as a human, also, if you give me the same set of images, I probably will be also able to classify that 99.9. I will be also having same accuracy. So in that setting, the performance of the human is very close to the machine learning algorithm. So when you come to this problem is far more challenging and interesting than that 1000 class problem. And the reason being, if I give this set of images to humans, they are not able to do proper classification. And what I mean by that is, we gave this set of images to experienced 3D printers who work day in, day out in the 3D printing domain, and asked them to classify in these 3 different categories that we have. And it turns out, average over 7 machinists, their accuracy for classification under these 3 categories came out to be 38%. Now, just think for a second. Even if you do random coin toss and randomly select one level for each of the category, what should be the accuracy? It should be 1 by 3, right? It should either 1 by 3. So that's 33%. The human accuracy was 38%. So it was as if they're randomly selecting and they have no notion what is happening in this problem and so on. So this is, even though this is a 3 class problem, this is a significantly challenging problem, because the human performance in this case is very, very poor and close to random guess that we have. So we use essentially a machine learning algorithm which is known as convolutional neural networks to basically recognize what is happening by just looking at the computer images. And once we are able to recognize, we will be able to do the process control as I mentioned. So again, here is a classical example of application of very recent techniques like convolutional neural network in a manufacturing domain, and now we are able to control the processes. Okay. So what I want to allude to this is, in this whole project, some of the things that I've shown you is, you can see there are cyber physical systems. You have a manufacturing systems. There are other cyber physical systems that are there, for example, autonomous vehicles, UAVs, unmanned aerial vehicles, and so on. And all of these cyber physical systems, we can use machine learning to do different things. It's not just classical software that we can use machine learning for designing, controlling, operating different physical things. Also, we can use machine learning, and that is what I want you to start thinking about, because that is a sort of a non-traditional uses of machine learning. Most of the times, you will see the uses of machine learning only in the software component, but going forward, I think and I believe that it's going to be more important for people to know this cyber physical system domain, where the cyber component or the software component is interacting with the hardware component, and people are able to create products which are far more superior and so on. Now, it turns out, when we are dealing with cyber physical systems, collecting data is typically a hard aspect. And I will give you an example. How many of you have used fridge in your house? Nearly everyone, right? I mean, okay, you have fridge, right? Fridge is a way, not a computer scientist, okay? And it has a rich history. So typically when you buy a fridge, right, it will operate without any problem for a long time, maybe 5 years, 7 years, without any issue it will operate, okay? So let's say if I want to use a machine learning algorithm to do anomaly detection to predict when the physics is when the fridge is going to go wrong and it's not going to work, and that is something that we can do using machine learning, we have to wait 7 years to get a single data point, right? And that's a physical system. So when we talk about machine learning and data science in physical system, collecting data becomes a big issue. It's time intensive, computationally intensive, money intensive. So now we need to be very, very judicious. How can we use machine learning algorithm in this domain and so on? So that is the area that I work in, and this is the area of basically where we want to use less amount of data and we want to use a system knowledge or knowledge of basic engineering background and combine them to create methods which we call this hybrid physics guided machine learning approach. And these are new class of machine learning approach we have been started working in last 4 or 5 years, where we are merging two different approaches. So I will explain this idea at a high level, but this idea is very, very important if you want to focus in the cyber physical domain and so on. Okay, so here is the thing. Traditionally, there are two ways to model systems in engineering. One is a physics-based equation. So how many of you have done dynamics model or you've done some sort of modeling in physics in class 12? All of you are engineers, right? You must have written some equation, force equation, momentum equation, conservation of energy equations and so on, right? So that's the classical approach of modeling. And actually that kind of approach is actually also used in engineering too. You write, those equations, you write ODs, PDs, and those are different types of equation. Now it turns out there are a lot of good publications in Science, Nature, very high impact journal, which are just focused on writing an equation about a complex phenomena that you have seen, but that set of equation beautifully explains what is happening, and nobody has been able to think the way that person has been able to think, and that's why they are doing it. And this is something that we have been doing for more than 200 years. So that's one modeling approach. But one caveat with this modeling approach is if your system becomes big. For example, if you have an autonomous vehicle, you have hundreds of different components, and if you want to create models for each of the component, it typically becomes very, very cumbersome to develop some of this system model. So what you start doing is you start making simplifying assumptions, you simplify the models, and once you start simplifying the model, the accuracy of this model is going to be, predicting accuracy is going to get reduced. However, one of the good properties of this kind of model is that they generalize really well. And what I mean by that is you might have observed the system operating in one or two instances, and based upon that one or two instances, you have developed this set of equations, but this set of equations generalize and explain everything about that system. Whereas on the second half, we have data-driven or machine learning based approach, which is an input to output mapping approach. And as I predicted and show you, and there are hundreds of different applications, if you have a large amount of data, then you can really get good results, good mapping, good accuracy. But as I mentioned, if you have cyber physical systems like cars, fridge, and so on, typically getting a large amount of data is not feasible, right? So we have to work with a small amount of data. That's one issue. The second issue with machine learning models, and this is something that you need to be aware, what is the limitation? The second issue is that they do not generalize well. So wherever you're training a machine learning model, they will work in that specific domain, and when you want to use that machine learning model outside that training regime, the prediction ability of a machine learning model is going to be poor. In fact, it will be so uncertain and bad that the system or whatever you're trying to do, it will not work. So that's one deficiency. The second other deficiency is very, very fatal and important for you to know, which is all of these machine learning models are not physics respecting. They are just input to output mapping function, but they do not have some very basic property of what is known as physics respecting. And I will give you a simple example so that you can understand this. Let's say if I'm modeling a UAV, right? By some simple physics, we know that the gravity always on Earth, for anything, the gravity is going to be pointing downwards, right? But this kind of simple things is also not being able to captured by any machine learning algorithm. In fact, if you just used a machine learning model of UAV flight dynamics, in some settings, it might say that the gravity is pointing upwards, which is a fatal, because then if you do that, and if you're building a controller on top of that, then if somebody is predicting gravity is up, the next step prediction is going to be wrong, and that is going to probably lead to catastrophic failure of that UAV. Now UAV is fine, it might drop, it break, it's not hurting, but let's say if you're using a machine learning algorithm in the next generation autonomous cars, and that machine learning algorithm is not able to capture the vehicle dynamics physics inside, and if you're making a prediction based upon that, then that catastrophic accident can also lead to deaths, right? So when we are building cyber physical systems, we need to be thinking that these people are operating, people are sitting in it, and people's life will be dependent upon it. They need to be respecting the physics that is out there. Okay, and this is the fatal flaw of current machine learning algorithms, that you do not respect the physics algorithm at all. So what they developed is basically a hybrid model, which is an approach to combine the physics-based model with a machine learning model together, and we have worked on this area where we have developed multiple different algorithms that allows you to take the basic physics that is involved in a system and then also place sensors on that machine and take the sensor data and combine both of their data together to create this hybrid physics guided machine learning approach. So again, I will not go through the technical detail. I just wanted to give you the idea, and this class of ideas are very, very vital for cyber physical systems design. But I want to quickly go through some of the examples where we are using some of these technologies and so on. So one of the area where we focused is in UAV swarms. Okay, how many of you have seen recent uses of UAV swarms? Anyone knows about UAV? What is UAV swarm? Multiple UAVs doing something. Not a single UAV, multiple UAVs doing something. Any light shows recently? So if you look recently in IIT Bombay, there is a team which has created essentially a swarm-based business where they can have a set of swarm which can do light shows. So they can arrange three-dimensional pattern, you can have different things. And this came out from China and other places too. They have thousands of drones that they can control the flight path, and that gives you beautiful shows that you can have in the sky. So they can replace the laser shows or fireworks shows, and these are becoming very, very popular. That's one application. But again, if you're watching latest Hollywood movies, in some of those movies you will see that the swarm drone is being used as a capacity for defense applications and so on. So they can have payloads and they can synchronize and they can attack different locations and so on, right? So there are multiple uses of swarms, which is multiple UAVs put together, or a flock of UAVs put together like a flock of bird, and you can control the flight patterns and so on, right? So there are multiple different challenges in the swarm domain, UAV swarm. And one of the challenges is like, we do not have a lot of, if the drones are small, we do not have a lot of hardware capability to be placed. Because if you place a lot of things, it becomes heavy and the flight path reduces or the flight time reduces, right? So how can we deal with this issue of very small amount of computation on board and process that real-time data so that we can control the swarm? And that's the focus that we want to work on. And here, if you do not have, hybrid physics-guided machine learning approach, if you're using classical machine learning approach, in many cases you will not be able to avoid the collisions, which is shown on the right-hand side. Whereas if you use the hybrid physics-guided machine learning type of approach, you will be able to process that information in real time and avoid collisions and so on. So that is one application of where we have applied the set of techniques that I mentioned, right? Now going back to again the swarm, there is a second application. I don't know whether this is visible or not, but essentially there is a UAV on top of other, and they are trying to come close to each other. So if you are in the UAV swarm domain, one of the things that you need to see, if you have seen it, when they are doing modeling or flight planning, one of the things that they do is they make an assumption that around a UAV, there is a big sphere under which second UAV cannot come. And why this assumption is made? Because if two UAVs are close to each other, they have basically this fans which are rotating at high speed, and that causes air drag, and they get sucked into it. So when they come close to each other because of that air drag, there is a non-linear interaction, and controlling the UAVs become difficult, and typically accident happens and so on, right? So what we want to do is we want to use this hybrid physics guided type machine learning approaches where we can use them to control them even in this non-linear interaction zone, so we can make that bigger sphere smaller, and so the UAVs can come and still be stabilized, and we can have stable UAV swarms and so on. So that's an application area where we have applied the hybrid physics guided machine learning. So even though UAVs are coming closer, we can basically take care of the non-linear interactions and so on. Here is another example, and this example is about identifying intruder UAVs. Okay, so now a lot of states are afraid that we might have terrorist group or other states or other nations who have access to UAVs, and these UAVs could have explosive payloads, and they can cross and fall down and so on, right? So one of the things that they want to do is they want to identify any of these intruding or adversarial UAVs that are in the flight so that we can shoot them down. Okay. So if you want to solve that problem, you can use machine learning to solve this problem. Computer vision, which is one field, which is image recognition. You can take a flight path and you can recognize the image and you can bound that box, and that will help you in identifying a UAV in a camera or in a picture or in a video, and that is you can do. But there are some specific edge cases where the classical machine learning algorithm is not going to work. And let me give you some example of that. Let's say if you have a white UAV in a white background, a completely CV-based approach or a completely classical machine learning-based approach is not going to be able to solve and detect that problem. And where that might occur? So I used to live in Buffalo, and it was really snowing and snowy and stuff like that. So if you apply a white UAV, there are snow, and you cannot identify the UAV that is there. Here, you can think about the same thing. Let's say if you're in Himalayas, and there are snow on the peaks and stuff like that, and if somebody is flying a white UAV, you will not be able to detect whether that UAV is flying by just images or so on. And where the terrorist or where the attacks comes from, probably hilly region where there's snow and stuff like that. So it's very important for us to recognize even in those tough conditions where the UAV is. The second example is flying a green UAV over a forest. Okay, the forest background is green and you got green UAV. So if you use classical machine learning algorithm, it's not going to work. You will not be able to isolate that. But the beauty is UAV is a physical thing, and it has a flight path, it has a flight dynamics. Right, it's moving. So you can process the images in such a way that you can create a physics of how the UAV is flying. And you can combine that information with the classical machine learning approach that is there, and that's where the hybrid physics guided machine learning comes into picture. You have now some extra information about the physics of the flight of the UAVs, and once you combine that together, you are coming up with the algorithms that can even detect UAVs in this adverse conditions and so on. So white on white, green on green, but there is a flight path that we can track, and based upon that we can identify which pixels are changing the flight and dynamics, and we will be able to identify them very, very reliably. So that's another application that where we are working, where we have used something like this. Okay, so here is an application where we have identified using this one, right? So what I want to do, come towards the last part of my talk, where I want to showcase what we have been doing in the last couple of years. Okay, so in the last couple of years, we have been focusing on this autonomous vehicle domain. How many of you know about autonomous vehicles? What they do? What is an example? Anyone? Yeah, you're good, right? So that's what we want to work on. So we want to create, and let me give you some perspective. What is going to happen in car industry? By 2035, all the cars that is going to be probably manufactured are going to be electrified. You will not see, probably by 2035, you will not see any petrol or a diesel car. Okay, and that has already set in motion for next 12, 13 years. Every car manufacturer is changing their production line and other things, and every vehicle that is going to be manufactured, at least from 2035 onwards, is going to be purely electric vehicle. So that's the next thing, and all the scientific work, technical work has been done. Now it's in the implementation phase. People will take 5, 10 years to implement it, and that's what is going to happen. But what will happen beyond that? Beyond the electrification of vehicle is going to be autonomous vehicle, driverless cars and so on. So we will be avoiding. And why? There are multiple benefits to it, and that's why we want to get to the driverless cars. So that's the area we work in, one of the specific areas we work in. And here what we have is we want to make an autonomous tractor. And I will give you some specific use case. This is a small scale tractor that is used for lawn mowing in the US. And this is a classical tractor that I use once a week or twice a week, once in 2 weeks to mow my lawn that I have. So grass grows and we mow this, right? So I drive this, there is a steering, I drive this, and in the bottom right here, if you see, in the bottom portion there is a blade that swirls and it cuts the grass there. Okay, so what we have done, we have got a funding from state, Department of Agriculture to make this autonomous. And what we have done is we have created hardware, software systems which can retrofit a given lawnmower tractor. And retrofitting means we are not going to change anything in the design. We are not going to design the system from scratch. We are going to take what is existing, but we will make it autonomous, right? So here is what we have done, and what we have created a prototype where we have made this lawnmower completely autonomous. So you can see there are some hardware, so, there are some actuators, and in the back you can see some computing infrastructures and so on. And just by using machine learning and some simple hardwares, you can convert and retrofit a thing like this and make it completely autonomous. This can operate in 2 different modes. Fully autonomous mode, we can take a where you can specify path A and path B. point A and point B in the path, and it will automatically go from A to B. Or the second mode, you can control this whole thing as a joystick, as if you are playing a video game. You can control it, and you can specify the path it needs to go, provided by the command of the joystick that you have to solve something like this or doing autonomy. It has to go through the steps of data science, machine learning, and AI. There's a huge amount of machine learning algorithm that has been used inside this for doing recognition, obstacle detections, and so on. And for path planning, there is a graph search algorithm like A star and so on has been used to do path planning. So if you have the knowledge of data science and machine learning, this whole domain of autonomous vehicle is going to be a fruitful domain to work in, right? So let me explain some other application of this, right? So why we want to create this? One of the possible application would be take this same thing, hardware software system, and increase the workload. So now we can take the same type of approach and create customized hardware which can work on fully large scale tractors. And if you do that, now we control the agriculture and we can do agriculture autonomously. Okay. One other application that is we are thinking of pitching this product as a market is basically lawn mowing alongside road networks of USA. There are thousands and thousands of miles of roads that are out there, and beside the road there is a grass that grows very, very tall because it's not maintained properly. So it looks ugly, and more importantly, it becomes dangerous because you cannot see if any other animal is coming from that grass and so on, right? So this is currently done manually. So somebody will manually drive this large-scale tractor on the sides of the roads, and they will basically cut the grass that is there on the highway. Now that is also not the best solution because sometimes there are accidents and other things, and people die because they don't see the tractor running and so on, right? So we can create an autonomous lawnmower for highways, which can first of all operate 24/7. It does not need light or something like that, and no person is operating that, so that we can save lives and other things, right? So that's another application we are thinking about expanding this project and working on. And I will give you some other application areas that might be interesting. I don't want to go too much into this system component, but I really want to focus on the yellow and the green rectangle that you see. Those are the perception unit and motion planning unit. And on top of that, you need sensors and motion control in order to enable autonomous system. But what is inside the perception unit and motion planning unit? The core is machine learning and AI. So if you have fundamental and solid knowledge about machine learning algorithms and AI algorithms, then you will be capable of creating something like this on your own. But that path definitely goes through you having a sound knowledge of data science, machine learning, and AI. Okay, so let's move on. Here is another application that we have been working on as a part of the same funding, where we are focusing on basically doing autonomous farming or precision farming in orchid farms. And let me give you this idea, right? What is this farm? This farm essentially produces peach, and peach is a kind of fruit that a lot of people in US eat. Especially in the summer, it's really good. In order to give you the context, it's very similar to guava in some sense, like crispiness and other things. So that is farmed, and thousands of hectares of farms basically have peach and so on. So one of the problems with this peach farming is that during the spring season, when the fruits are coming out, you have to fertilize them. Okay, what is the current fertilizing approach for these farms? Treat all the trees equal and spray the same amount of fertilizer to each of the tree. Okay, so there is a tractor that comes and there is a big sprayer. It does not differentiate between different trees. It does not differentiate. It is mercilessly sprays the same amount of fertilizer on all the tree. So what we want to do is we want to go through a second approach where let's take the same autonomous tractor that you saw, and let's mount a camera on top of that autonomous tractor. And now first we will go through the orchard farm. We will take images of each of the trees, and using machine learning we will count all the peaches that are there in each of the tree, and we will also see the size of the peaches that are there. Okay, so we'll get some notion of how many peaches are there and some notion of how big the sizes of the peach are there in the each of tree. And then we can create a simple model to find out exactly how much fertilizer that needs to go on that tree. And this way, we will move to what is known of this notion of precision farming. We can precisely spray the amount of fertilizer to a specific tree rather than mercilessly doing equal amount of fertilizer, right? So in order to create some applications like this, how do you do that? So you have to create a path planning algorithm where the autonomous vehicle has to go through this autonomously, right? So I'm going to show you some videos is how intelligently you can use machine learning and concepts from there to create a very good path planning algorithm. Okay, so this is a video. You will see that we are using a CNN or convolutional neural network, which is a machine learning algorithm, which given a set of images automatically identifies the trunk of a tree. So we are focusing not on the leaves, we are focusing on the brown portion which grounds the tree, right? The trunk, the brown big trunk, that's what we are focusing on identifying. So once we have identified that, what we can do is something like this, where what we will do is in the image frame, when we are identifying the trunks, here the trunks are identified as this red rectangles that you have. In the camera frame, each of the identified trunks becomes basically a red dot if it is on the right hand side, and a blue dot it is on the left hand side. And then I can basically draw different edges between this circle, and these edges will essentially intersect somewhere in the middle right here, right? Multiple different edges will intersect. So if you draw a line, let's say 4 lines from here to here, here, and so on, and similarly you connect all the nodes that you have seen in this, it says essentially create a lot of intersection of the edges right here. And that could be basically connected through all a straight line, and that gives me a notion of how to do a motion planning. So you can see what we are going to be doing is we are now identifying all this, and based upon this, whatever we see in the camera frame, we are changing the straight line which is connecting this set of edges, and that will give me a motion planning algorithm to precisely go through the middle of the orchard farm that we have. If you don't use something like this, maybe the autonomous vehicle will be going like a serpent, right, from here and so on, and that's not the most effective way to do this, right? So now, in order to implement something, a path planning, something like this, what is the key thing that we have done? We have been able to identify the trunks, which gives me the notion or localizes where the vehicle is. And localization is a big problem. The vehicle needs to understand where it is in the context of the environment that is out there. And in order to enable some localizations like this, right, you have to use machine learning. This is a classical application of convolutional neural network. In fact, we have used YOLO 7, which is like one of the latest version of object recognition to do this, right? And all this whole path planning and other thing that you see here could be enabled based upon the machine learning algorithm that we have. Okay, so with that, I will, stop, and I can take any questions that you might have. But before I do so, if you have any interest in cyber physical systems or automotive things, or in general AI and machine learning in particular, then I will recommend you to connect with me on LinkedIn. I typically post very innovative information of AI, machine learning, and so on. So if you want to continue the information that you have seen, just connect. And with that, I will take any questions that you might have.
Yeah, the forum is open for any questions if you have. We'll hand over the mic to you. Students.
Don't be shy. I mean, if you have any questions, you might get some interesting perspective. Okay.
Are you with me, sir?
Yes, go ahead.
Thank you for your presentation. But when you were presenting on this autonomous or software or the development you have just presented, I didn't hear anything about security, because this is something that is autonomous, right? So what are the security measures that are in the system that you have built? I didn't hear anything about security, because security is one of the paramount concerns in these designs.
So if I'm understanding your question right, you're saying that what are the security, so security from the accident, security from the cyber security, what kind of security you're talking?
Security from the cyber perspective.
Yeah, sure, yes. Any cyber physical systems will have security concerns. So let me talk about that. So that's a very good question, right? Interesting question. So you need to start thinking about, when we are creating cyber physical systems which are intelligent, autonomous and other things, one of the things that we also need to think about, that people can hack into this, right? So there is a lot of information that is passing out from actuators, sensors and so on, and this is basically done most probably through wireless communications and so on. So somebody can actually hack into the data and maybe can control that whole vehicle. So if they can hack into your system, rather than you controlling, they might be able to control it and operate it. Now let's say if there is a terrorist person who hacks into it, then he can, basically guide this to do attacks on other people and so on. So that's a valid thing. So cyber security is a major aspect that you need to think about when you're creating a systems like this. And then there are provisions and other things, right? So you need to go, again, this is a big branch in computer science and electrical engineering, where people are thinking about how to create, cyber attack resistant systems and so on. So there's a lot of research being done, and in most of the cases they're putting different measures for you to protect against cyber attacks and stuff like that. So again, that's a specialized field, and that you need to place certain measures in the cyber physical system so that it cannot be hacked and so on. Okay?
Anybody has any other questions?
Afternoon, everyone. Sir, we have discussed how machine learning and everything help us. Like in the starting, you have explained that in Facebook and everywhere, ad recommendation is also based on machine learning and all. So we see that not everything which is available online are great things. Like some negative things are also there on the internet. So if machine learning is set means to work on itself, like to learn from things which humans do. So most of the time they do great and things which are commendable, but sometimes wrong things or negative things are also done. So what if the machine do learn from it, or try to capture it for learning itself? So how we are means
Sure, I got that. Let me rephrase what you're saying. So you're saying that obviously there are good potential uses of machine learning in various applications, but the same sort of technology could be also misused, first of all, or if system is basically fully machine learning, it could have its own conscious or sentient, and it can do wrong too, right, and so on. And so this is a common concept that is there. And there is a lot of research being done exactly on this topic, where people are thinking about, what are the, there are various researchers who are thinking about how could machine learning would be misutilized, and what are the other things that we can do in our place in the system so that they cannot be misutilized and so on, right? And again, recently, if you saw in the news, one of the Google engineer who came, he basically mentioned that the current Google system has some sort of sentient, and it has its own notion as a child-like brain, and it can probably act independently of what it's supposed to do and so on, right? So that's a valid concern, again, and it can happen and so on, but people are researching and trying to find out and minimize and mitigate that. And this is a technology, that this technology can be also in the hands of a good person, and this technology can also be in the hands of a bad person, and so on, right? Lot of cyber crimes and stuff like that. Lot of chatbots are machine learning based chatbots, right? It's basically a classical application of natural language processing. You think that you're interacting with a chat, but that's a person, but that's not the case. It's a machine learning algorithm interacting with you and giving you all the answers that you have. And many of the frauds that happens, the financial, where they're taking account information and so on, they are basically based on automated chatbots and so on and so forth, right? So that's one misutilization of this kind of technology, and people are looking forward and researching ways to mitigate that kind of bad impact. But that's a valid concern, and that is going to be a concern that we need to look forward to and try to mitigate to.
Any other questions? Anyone?
Good morning. Thank you for this.
I'm not able to hear you. Can you be loud?
Oh, can you hear me now?
Can you bring the mouse, mic close to your mouth?
Okay.
Yes.
Okay, thank you for this chance. I wanted to ask, for example, if we have a service and we implement a ML on it, and for example, if it's taking information data from the user interaction from a service, and how do you filter not all data are useful, right? How do you filter those are useful data to learn from, and which are not appropriate or useful enough for it to learn from? So which information or interactions are useful enough for it to base this learning upon?
Okay, thank you for your question. Unfortunately, I was not able to hear everything that you said, but let me try to rephrase what I understood from what you're saying, and hopefully that is the question. If not, then you can come probably down and I can listen to you. So if I heard whatever I got is that there are multiple different things that we can feed into machine learning algorithm. There are multiple sources of information that we can feed into machine learning algorithm. How do we determine which one is the important aspect to put in the machine learning algorithm, right? Is that the question? Okay, so if that's the question, that's an easy answer. The answer is there are many classical techniques, there are many different techniques that are there in the machine learning domain that does what is known as a sensitivity analysis. So with respect to the input that you provide to that machine learning and the output that machine learning gives, you take that, how much that input influences the output. This is a measure or notion what is known as sensitivity, and you can measure this sensitivity using classical statistical technique like AIC, Pearson coefficient, Spearman coefficients, and you can compute those, and those tells you the importance of the each individual input with respect to the output that you have. Okay, now once you can use any of, there are multiple of them, so you can use any of this coefficient and you can compute this sensitivity, and that will give you a priority or the ranking of the top most important features or the top most data that influences the prediction you have. Now, so you can create a rank and list them, and if you think that you only want to pick the top 10 based on this information, you can pick up the top 10. And these coefficients also give you a notion of how that input is important. Some of them might have very, very low values, so that tells you that they are not impacting the output at all, and that's how you can weed out or filter them out. Does that make sense? Okay.
Sir, at first, so thanks for giving such a fruitful information about all this machine learning and machine learning algorithm. Sir, my question is that as we know that in day by day, there is a increasing rate of unemployment in every sector. So if that very autonomous technology will if used in larger scale, then what would be the difficulty for a nation to handle that very unemployment rate?
Okay. So the question is, if the machine learning is automating a lot of, again, I'm rephrasing questions just to make sure. So give me a thumbs up if I understood your question right? So the question is for everyone that if we are automating a lot of things and doing autonomous vehicles, and we have a nation where a lot of people are there, we might be creating unemployment and so on, right? Is that the question? Okay, so I understood the question, right? Yeah, that is a possibility. But here is another perspective to think about. Okay, typically, and this is a classic example in engineering domain. In 1930s, we used to dig ditches using powders. Okay, it used to take 3 months, 4 months with thousands of people to ditch a dig where we can do some tall building. Now we have these JCBs and other things which are sort of a technology version of digging ditches. Has that replaced the job? No. In fact, that has accelerated the growth rate, created many more opportunities for employment and so on. And let me give you an example of how this is going to create more employments. Okay. For example, let's say the example that I showed in UAV domain, right? There is going to be huge. So one of the projects that is also happening in India too, and also in US and other things, where people are looking about how to use these autonomous vehicles or UAVs for farming application. One of the application I know which is very, very popular recently, if you know, IFCO has patented UAV which can carry essentially 10 liters of fertilizer. Okay, and this is based on nano urea technology. So and it can fly over this and it can spray fertilizers. Okay, now people are thinking, if that's the case, then we will replace the person who is doing the farming and fertilization. But who is flying the UAV? Who is maintaining the UAV? There is a set of pilot. UAV is not flying. You need a pilot to fly that. You need a maintenance person. So there is a cohort of 4 or 5 people who support this infrastructure. What we are going to do whenever the technology comes is, we generally have this notion, we are afraid that it might replace a lot of people, but at the end of it, it always ends up creating a new possible sectors of service and so on, where people typically get absorbed and they find employment. Most of the times, not all, but most of the times, a new technology creates more job than the previous opportunity that you had, and more importantly, it accelerates the growth that we have, right? If you're still not using JCB and trying to do the modern construction building that we have using 1930s, right? We will not be able to do and make that kind of progress. So that's why technology is needed, and many of the things, right? It will create more jobs for sure. And here is another way to think about. There is an area that I worked in 2001 and 2 called artifact system. So it's not just a system. When you do a product, things are connected with it. And I will give you an example. Let's say if you create a car, right? Just in order to operate a car, people started creating road networks. You have to have roads. Once you have the roads, oh, we need a gas station, petrol station. Oh, we need a dhaba to eat there, right? So just because a car, there are so many things which are connected, are created, and that creates the the flux of jobs that comes around, right? So again, autonomy as a general principle is a technology, but what it will do, it will create a set of products, and each of these products are going to create their own artifact system where people could be employed and so on, right? So it's always, you have to think in that sense that typically, in general, onset of a technology is never hurting humans. Most cases, it is helping, accelerate the development that we have.
Others? Do you have any question?
Yes, sir. I have heard that the AI models need more data to improve their model. And so, as a student or a small company, how can they get more data, big data, to improve their model?
Sure, that's a good question. It's a practical question, technical question about machine learning and AI. And I sort of alluded to that in my presentation, because the question is like, typically to get a high performance and use the latest and greatest techniques like deep neural networks and so on, you need a large amount of data, and that will give you the accuracy that is needed. So how, as I said, like in many cyber physical systems, you will not be able to do that. And so this is a fundamental research question a lot of people are asking. Okay, and I propose the solution in the form of cyber physical systems where you have physics-based model. You can leverage that information, and you can merge that with a machine learning algorithm. But that is not necessarily just a single approach. There are multiple different approaches. So I will give you some techniques. Okay, I will talk about both things. First, how can you create data, and how can you enlarge your data? So you can be creative in expanding and augmenting your data sets. So there are something called this whole field called data augmentation. Okay, and let me explain what this means. So let's say if you have an image, right? Single image, and if there is a cat that you want to identify in the image, right? If you take that image and if you rotate that image by 90 degrees, still the same cat is there. If you rotate another 90 degrees, still the cat is there. So only by simple algorithm where you rotate that image by 15 degrees, 15 degrees, 15 degrees, you are able to create the 6 different copies of data where the pixel location of the cats are different. So there are huge class of this data augmentation techniques you should be looking for that help you in increasing the small set of data and making it bigger. And this is artificial augmentation. But they have the same information, but the pixel information is changing, location is changing, so it becomes a new data. So that's called the data augmentation technique, right? Second thing, look into applications where you might have interesting way of creating an automated data. You can write a script or something like that and automatically create. For example, in NLP domain, it's very easy to write a specific web crawler with a set of keywords that can crawl the website and give you the large amount of data. Internet is huge data. You can write specific web crawlers to scrap the data from there, and that could give you a big data. The example problem that I showed about the manufacturing feature recognition, the machinist one, what we did, we hacked into the SolidWorks API, we wrote an automated code which generated thousands and thousands of data. So if there is any way you can automate the process of data generation, then you can shift this task to computers and they can generate a lot of data. That's one approach, right? So this is taking care of the input and inflating the data set that you have, which is known as data augmentation. The second approach is you can focus on techniques which takes less amount of data. Okay, so I will give you some techniques. There is something called few shot learning people have developed. Okay, I give you the hybrid physics guided approach that will work on a less amount of data. Few shot learning. GAN, generative adversarial network, is another class of techniques which work on less amount of data, and that give you a very fairly highly accurate and so on, right? Transfer learning, in some class of problems, you will be able to use transfer learning with a small amount of data to do a lot of different things. So multiple different approaches are out there. It's just that you have to go through the nitty and gritty of it, but there are multiple ways to deal with the low amount of data. And here is another more important thing. Not in all applications you need a very high accuracy. So if you have small amount of data and if you just know the classical machine learning approach, that will do wonder for many of the applications that you're interested in. Okay? Okay, so those are the 3 things that I can tell you at this point of time. Okay, so if you have any questions, and again, since I visited here, so connect with me on LinkedIn, send me a text message if you want to know more. And since I visited this place, I will definitely recall where you come from, so I should be able to address and answer some of your queries you might have. Thank you everyone for listening. You're a wonderful crowd.
Thank you, sir, for wonderful session. I'm sure our faculties and students will surely be benefited out of this. We saw example ranging from small devices to autonomous car, and yes, the last part added, few shots learning and adversarial network. Many students are working on that. So thank you for all the insights you have presented. We'll surely connect with you and do a good work in this area. Thank you, sir.
Thank you.
I would request students to check their official Telegram group to know their further schedule of the day. Okay? You can slowly disperse from that side.